Hans Christian.
At least we got a mathematical expression for this one right now. We got it from the Ampere's law. Okay, Ampere's law is a simplification of Biot-Savart's law. All right, so Biot-Savart's law is something that we will get into for derivation. So Ampere's law is what we looked at already. Speaking of the Ampere's law, kind of like the yesterday's setup. All right, so speaking of the Ampere's law, this is the major formula right here. All right, so the circulating magnetic field that we're looking at is going to be responsible for the net current within the Ampere. All right, so the circulating magnetic field in the counterclockwise direction, the net circulating magnetic field in the counterclockwise direction is going to be due to the net current inside the Ampere loop that you're looking at. So that's what the Ampere's law states. If the current is coming out of the page, we will take that to be a positive current. If it's going into the page, we will take that to be a negative current. So this represents the net current, which means that you're just summing up all the current values.
Is the same as the force between two current carrying wires.
Okay, so when the currents are in the same direction, there's going to be a magnetic attraction. When the currents are in opposite directions, there's going to be a magnetic repulsion. Okay, Roderick, what kind of background noise are you talking about?
I don't know. I keep on hearing people talking, dancing, or some noise. I don't
know. My wife is working out.
Oh, okay.
Oh, hold on. Hey, keep it down. People are getting upset. I'm just giving you a hard time. Evidently, they can hear you. Hey, Roderick, if there's a divorce attorney.
Sorry.
Yeah, I have to let her work out, man. Okay, so she decided to take it down. All right, good feedback. Give yourself 5 points. Anyway, so we got ourselves a solenoid. Okay, the formula that we were looking at indicates that the strength of the magnetic field at the center is going to be constant. Inside of it is going to be constant. Okay, so that statement is only correct only near the center of a solenoid, because most of the physics derivations assume that this is an infinitely long solenoid. There is no such thing as something being infinitely long. All right, so this is one of the derivations that we're going to take a look at shortly. This is going to be a really simple one. And then you take a solenoid, turn it into a toroid, so it's a donut-shaped solenoid. So the strength of the magnetic field is going to change. All right, depending upon the radial distance. The weird one is this one. The strength of the magnetic field for this one is going to depend on the current value. It's going to be inversely proportional to the radial distance, obviously, with respect to the center. Radial distance of the current loop with respect to the center. So that's what it says. But how do we come up with that formula? Well, forget that formula. Let's take a look at the application of it. All right, so this problem number 3 is the one that I'm interested in. All right. Okay, so problem number 3. The current is going up, and then it makes a tiny little loop, circular loop, and then it keeps going back up again. Okay, so what would be the strength of the magnetic field right at the center? So C is going to represent the center. Okay, so you got the current going up, so you got the straight wire, and then makes a loop, and then continues to go up. Okay, so we got a bunch of numbers here. The current value is 8 amps or whatever, so I don't care about the numbers right now. Let's come up with some kind of a mathematical expression that's going to give us the total value of the magnetic field at the center. So what would be the total value of the magnetic field right at the center? All right, so this is problem number 2. Or problem number 3, okay. Problem number 3. Okay, so this thing is going to look like this. It's going up. So the current is going up. And then it's going to make, messed it up. Oh, cute, almost worked. And then it's going to continue. All right, so Okay, nice. Okay, so let's figure out the magnetic field strength right at that point. Okay, the straight wire is going to cause a magnetic field. The magnetic field due to the straight wire is going to go right into the page. Okay, I forget that. All right, so with respect to the straight wire, it's just going to go into the page just like that. And then also this is going to cause a magnetic field. Magnetic field going into the page. And then this wire is also going to cause a magnetic field. This time it's going to be coming out of the page. Okay, so this portion of the current, B straight, okay, that sounded weird. B sub S for the straight wire is going to be going into the page. And the circular portion is going to be coming out of the page. Okay, so BC is going to be coming out of the page. So BS is going to be going into the page, and BC is going to be coming out of the page. Okay, so that's what we got. All right, so the component of the magnetic field due to the straight wire, I'm going to call that B sub S, straight wire. And the component of the magnetic field due to the circular portion, I'm going to call that B sub C. Okay, so if it's coming out of the page, let's use the assumption. If it's coming out of the page, let's assume that this is positive. If it's going into the page, let's use the notation that that's going to be negative. Okay, so let's figure out the total magnetic field. So the total magnetic field at point C, the center, is going to be the magnetic field coming out of the page, which is due to the circular portion. And the component of the magnetic field going into the page, we will take that to be negative. Okay, so that's it. Circular portion of the magnetic field is due to the current in the circle loop. And the portion which is responsible for the straight wire is going to be the same current divided by 2 pi r. All right, so this goes there, and then substitute this into that formula. So the net magnetic field right at the center, I'm going to just do the lazy thing, factor out the common terms. The entire thing is common on both of them. So the only thing which is uncommon is the pi. All right, so what do we have? So this entire term is going to be on here. All right, so B sub C is going to be 1, and B sub S is going to be 1 over pi. Okay, that's it. Sum them up, and that's what you come up with. All right, so this is how you do problem number 3. If this were a test question, obviously you would do it numerically. Again, this would be a multiple choice quality question, difficulty-wise. All right, before we do the derivations, okay, I'm gonna kind of back up a little bit. Okay, what is it that I'm interested in? The strength of the magnetic field. What happens to the strength of the magnetic field inside a wire and outside of a wire? Okay, so that's what I'm going to be interested in. Okay, let me find this in PowerPoints, because that's the derivation that we will need. Okay, so we'll get back to this. All right, so this is the sort of stuff that requires a derivation, and this is actually cute, because if I make a few adjustments to this one, it can turn into a really cute extra credit problem. All right, so let's just go over it real fast. Just want to show you how to do this. All right, so part A is straightforward. We'll start out with part A, and then we'll move on to part B. Okay, more than likely, the problem that I'm going to give you usually may not involve numbers, okay, which means that it's going to force you to actually show your work. It makes it almost next to impossible to cheat as well, and it turns into a real physics problem. When I say real physics problem, the sort of stuff that we normally do in real physics, because we don't get these kind of numbers usually, unless it's an experimental setup. All right, so what is the strength of the magnetic field right at this center? All right, so we got a straight wire. All right, this is not a straight wire, so let's just do this. Let's do it again. All right, so it's got a radius. And what I'm interested in is this is a current wire, so there's going to be a certain amount of current coming out of it. And R is going to represent the radius of the wire. So what I'm going to do is I'm going to place my Ampere loop right here. All right, and we are looking for the strength of the magnetic field right at the surface. Okay, so we're looking for an expression for that one. The way to do this is you just have to use the Ampere's law. All right, so you got your ds and you got B. Okay, in this case, B is going to be, if the current is coming out of the wire, I got to change colors here. All right, so the current is coming out of the wire in this case. I is the current. We got the Ampere loop. Okay, I'm going to make this ds in the red color. And then let me see which color I want to use. All right. And the magnetic field is going to be B. It's in the same direction. The current is coming up. All right, so that's the direction of the magnetic field. Okay. All right, so direction of the magnetic field parallels the direction of the Ampere loop. So we will actually do the integration in the counterclockwise direction. So the angle between them is going to be 0. Okay, so when you're looking at this, in terms of a dot product, this angle that we're looking at right here, this angle is going to be 0. Because that angle is 0, this is going to give you, cosine of 0 is going to be 1. All right, so this is going to be 1, and which means that now we can go back and use this expression in its scalar form. Okay, so obviously, you're looking at the strength of the magnetic field at a given radial distance. All right, so this is the radial distance for that magnetic field, so let's just indicate that. So there's no confusion. Okay, so lowercase r is going to actually locate the magnetic field for you. All right, so, and notice that the strength of the magnetic field at this distance is going to remain constant, so which means that I can pull this out. And the integration of ds. Okay, so this integration of ds, if you actually complete the loop, it's going to be the same as the circumference, which is going to be 2 pi r. Okay, so solve for B. This is going to be r, lowercase r. Okay, guys, this lowercase r is going to equal to the radius of the loop. All right. R is the same as the radius of the loop. As a result, this is the expression that we end up getting. All right, so this is the strength of the magnetic field right at that point, right at the surface.